How we doing? Good. Good. Any questions about anything at all before we continue on? All right. So last time we were just starting to set up what we're going to do with Fourier series. So again, we've already talked about doing least squares ideas. That was what your homework that you just turned in was all about. Trying to find a function that best fits a set of points. What we're doing now with Fourier series, the concept is that we want to try to find a function that approximates another given function. So we're in a function space now rather than in just Euclidean vectors, Euclidean space, looking at points, maybe two-dimensional points, maybe three-dimensional points, what have you. We're changing over to trying to do function approximations. All right. So, pardon me. The idea, again, behind least squares from a geometric standpoint is trying to minimize an error idea. And we talked about this last time, that if you're trying to minimize an error idea, really you're trying to make a distance being as small as possible, given a space that you have. So in a Euclidean sense from a picture, if I've got some, say, two-dimensional space, whatever that happens to be, and I'm trying to approximate some other vector that sticks off of that space as best as I possibly can in that plane, then we're going to try to do this one down here that comes down perpendicularly. And in this spot, we would refer to this as the projection. If I call this V, and I say call this space W, then that projection vector is the one that I'm looking for. That's the best one that I can possibly find. Okay? That's a picture in a Euclidean sense, right? If I've got a set of two-dimensional vectors that span some space, I can do all the linear combinations of those two-dimensional vectors in the space. Then the best approximation that I can get of that vector that's sticking out of the space is trying to find the one that has that shadow there, right? Project it straight down onto the space and use that. Okay. So the idea is to try to figure out what this projection is. And again, we want to try to do this more generally than just talking about doing two-dimensional spaces like I drew the picture. I can't really draw better than that. Okay. So far as being able to draw things. Okay. All right. So again, the idea here is that our goal here is to try to figure out what that projection is down to that space. To get to that point, if we have a set of generating vectors down here, I'll call them W1, W2, out to Wn, generate that subspace W. I'm not going to spend a lot of time generating or doing the theory behind this. But if they generate W, we refer to that as a basis. That's what we call a basis if it generates the space. And they don't have extraneous information in there if they're linearly independent. If you've had linear algebra, you've heard those words before. If you haven't, and take linear algebra, you'll hear those words at some point. Okay. All right, so if they generate W, by generate I mean they are linearly independent, meaning there's not any extraneous information in here. I can't write one of them in terms of the others. And generate everything in here. I can write every vector that's in my space as a linear combination of those things. So if I have a generating set like that, and the vectors in here are what we refer to as pairwise orthogonal. Orthogonal is a fancy word for perpendicular. Perpendicular we can check with a dot product or an inner product. So if everything here is pairwise orthogonal, if you think about if you've had Calc 3, for example, if you've got your vector, or even physics, probably talk about in there too. If you talk about your vectors I, j, and k, those vectors form what we refer to as an orthogonal basis for R3. Everything in R3 can be written as something times I plus something times j plus something times k. Right? There's only one way to do it. Right? If you have an ABC, you write it as AI plus BJ plus CK. That's it. Right? And if you check, these vectors are perpendicular to each other. That's what I mean by that orthogonal basis idea. So that's all I'm writing here. If I've got some space, just call it whatever it happens to be. We're going to be dealing in function spaces. That's where we're going with this Fourier series stuff. If I have a space that has this orthogonal basis, so that's basically what I'm writing here with the sentence that we have, then this projection vector of V onto W can be found by doing these inner product ideas. I can take my V, dot it with W1, divide by the length of W1, and then do W1. Notice this, we talked about this last time. This looks like your projection formula of a vector onto W1, right? Right? And we just keep doing this all the way through all of those basis vectors. You can just set it over there in the table for me. Thank you. Okay. So this is a way that we can find the projection of a vector onto a subspace if we have an orthogonal basis. It's important to have an orthogonal basis here because we want to be able to figure out these coefficients easily. That's why we need orthogonal basis here. So in linear algebra, one of the things that you do to try to, if you don't have an orthogonal basis to start with, is to do an orthogonalization process called the Gram-Schmidt process to get an orthogonal basis. But this is why we care about orthogonal bases, is because we can get these projections by doing dot products, which allows us to find least squares solutions. You already told me before, just from an intuitive sense, that if I'm trying to approximate this vector not in my space as best as I can by using things in my space, then I want to look at that projection down, that perpendicular projection down, right? So this allows, if we have an orthogonal basis, this allows us to find that projection quickly, relatively quickly. Okay. All right. So you can do this actually with least squares ideas that we just talked about in the previous section, or the previous one that we talked about. You can do it this way from a geometry standpoint, but it makes more sense to do this, at least for our purposes, not necessarily to do that when we've got Euclidean vectors, because we've got other ways that we can attack it quickly. But we're going to do this in function spaces when we're trying to get approximations of functions using other functions. And so that's where Fourier series come from. All right, so for Fourier series, and I know it looks like Fourier. It was Fourier, and then it was Fourier. And then maybe you get Fourier. Sorry, bad joke. It's fine. Okay, Fourier, French. Okay, so Fourier series. The idea here is that we want to approximate, because we're going to stop these. A series is an infinite thing, so we're going to stop it. So really, we're going to use these things to approximate. We're going to approximate periodic functions with what we refer to as trigonometric polynomials. That's the whole idea of Fourier series. So just to give a little bit more of the conceptual part behind things, I need to talk about how we define what we mean by a dot product when we're talking about functions. Okay? All right, so let's do that a little bit. So we're going to consider the space, I'll call it, usually I use V for vector space, so I'll let V be this space. So this is our notation. This is the notation for the set of continuous functions on the interval from A to B. So when I use CAB, I mean the things that are that if I could have a dot filled in at A, I have a dot filled in at B, and all the dots in between are connected. Okay. So functions that you can draw starting at A, ending at B without lifting your pencil. That's what that space means. Notice I didn't say anything about differentiability, right? I'm not saying it's differentiable. So you can have all sorts of things that are sharp corners or cusps or those kinds of things. But everything is connected from left to right as you go from A to B. Okay? The reason why we want to do the set of continuous functions is because if we have a continuous function, then we know that I can integrate. And so that's where our inner product idea is going to come from on this space, is from integration. So when I talk about two functions, I'll say f and g. If these are in my vector space, so if my f and my g are in V, then we define the inner product or the dot product of f and g as the product of the two functions and then integrate. So you take your f times your g and integrate over A to B. So that's how we do an inner product here. Inner products are dot products. That the word means the same thing. Inner product is more fancy. We use dot product when we're talking about Euclidean vectors. Doesn't matter what words you use. Inner products are used to assign lengths to vectors. And from assigning lengths to vectors, you can get distances between vectors, you can get angles between two vectors, and all of those kinds of things. That's why we assign inner products on spaces, if we can. So this happens to allow us to get what we mean by the size of a vector in this particular space. Think about how you do size, magnitude of a vector in Euclidean space. If you said, for example, your vector v was 3, 2, -5, then the way you would get the length of v would be you do the square root of each of the components squared, right? Right? But another way to think about this is that underneath that radical, that underneath of the radical part is that I really just have the dot product with that vector with itself, right? Many of you have me for linear and have seen this just recently, right? Okay. All right. So anyway, that's the whole idea. One of the whole ideas of why we want to have an inner product idea defined. Remember, again, we're trying to think of this from a least squares idea. I want to try to minimize this error in here, right? In order to minimize that error up there, I need to know something about how long it is, right? I want to make that distance as small as possible, okay? And we agreed that we can make that distance as small as possible if I do projection. But in order to think about as small as possible, I better have a length in another space if I'm not talking about Euclidean vectors. Okay, so I have to have a way to define length. And that's what inner products do, is allow us to define length. Again, inner products also allow us to do angle things. And notice that these things are, like we said over here, these things are mutually perpendicular. You can check perpendicularity or orthogonality by doing dot products. Okay, so this is what we can also use this idea in a function space in our continuous functions on the interval from A to B. We can use this idea to allow us to talk about orthogonality as well to help us to get to this projection idea. All right, so we're not going to actually verify that this really does satisfy what we needed to satisfy for inner product. However, I will mention that if we think about length of vector as square root of a dot product with itself, The reason why we want to make sure that we have that always positive is because of that square root idea. And if I do a dot product of a function with itself here, this is going to give me the function squared. If I integrate a square of a function, it's never going to be negative, as long as it's continuous. Okay. All right. So in any event, that's one of the reasons why that's one of our properties for dot product, is so that we can actually define lengths. Anyway, I don't want to go too much into the weeds with concepts, just tell you where these things are coming from. All right. So if our goal here is to approximate periodic functions of trig polynomials, the idea here is that I want to try to create a subspace, a smaller piece, because not all continuous functions are periodic, right? Right? Periodic means it repeats, correct? Okay? So not all continuous functions are periodic. We're interested in doing this on a piece of this space, the ones that are going to be periodic, or a piece of what we say continuous, well, they don't have to necessarily be continuous everywhere. But anyway, we're going to do this on a subpart. So what we're going to do is we're going to create a subspace that's generated by a set of trig functions, and then use that subspace to project onto. That's our whole goal. Okay? So when we say things that are a trig polynomial idea, what we mean is that we're going to consider these functions. I'll start with a function, a constant function 1. Then we'll do sine x and cosine x. And then sine of 2x, cosine of 2x. And continue this idea. Increasing that coefficient by 1 each time. So we would have sine of nx, cosine of nx, and so on down the line. Let's consider this as a set. If we do a finite sum out of this thing, what I mean by that, of course, is just pick a finite number of the functions. So I don't have an infinite sum, but a finite sum. If I do a finite sum of things from this and do linear combinations, remember again, linear combination is constant times function plus constant times function, or constant times vector plus constant times vector, and so on down the line. If I do a linear combination of a finite number of those things, that's what we mean by a trig polynomial. Okay. But let's consider this particular set. One of the things that we can notice here, I'll do it this way, since I'm going to start playing with it anyway. One of the things that we notice is that this set really is orthogonal. It's an orthogonal set. So remember, to be an orthogonal set, we would need to show that anytime I take any function and do the inner product with another function that's not the same thing, I get 0 every single time, right? So we should verify that we really do have an orthogonal set here. I'll write that back down. Let me go into GeoGebra here, because we're actually going to use GeoGebra quite a bit to help us with the integrals that we're going to be doing to get these Fourier series. So going back to GeoGebra Classic, I want to make sure that I open up the computer algebra system here when I do this, so that it'll integrate symbolically, because we're going to want to analyze these things as we go along. So let's start with, I'm going to do, first we're going to start with functions that are periodic on the interval from, let's do 0 to 2 pi to start with. Doesn't really matter, but we're going to do 0 to 2 pi. We'll have to make adjustments to coefficients if we change the period to something different. So let's start with functions that are periodic on 0 to 2 pi. And I want to show that all of these things are orthogonal to each other. All right, so the command for integral in GeoGebra is literally just integral. So I just start typing int, it pops up. Notice you've got lots of options here. It doesn't matter really which one you select, as long as you fill in what you want each time. All right. So I want to show that let's say any sine times any cosine, the integral is going to be 0 over 0 to 2 pi. Okay. So I can just type in sine of, let's say, m times x, and then cosine of n times x. Now, either in GeoGebra, you have to be careful, just like when we do things in R or do things in Python. If you put letters next to each other, it's going to treat that whole thing like it's a variable. So I really want m times x and n times x. You can do that just by putting a space between them. A space between will do multiplication, or you can use the multiplication symbol, a little asterisk. All right, I want to integrate this, but notice that I have 3 variables here, right? I've got an m that it doesn't know, I've got an n that it doesn't know, and it has an x that it doesn't know, correct? Okay, so I needed the next thing I need to do is tell it what variable to integrate with respect to. I'll put a comma and then an x. I can zoom in a little bit. See it a little better, maybe. And then I said, let's consider the periodic functions on 0 to 2 pi. So I'll type in my limits 2 and pi. I notice again, every time I've got a multiplication that I'm doing, I've been putting a space in between. M times x here, I put a space between for the 2 functions. N times x there, 2 times pi there. Some of them it'll interpret correctly. I didn't really need one here. And I didn't really need one here because it would interpret both of those correctly. But just to get in the habit of, put a space where we want multiplication, it won't go wrong. All right. Again, if these are going to be orthogonal to each other, I should get 0. Notice it came up with a lot of stuff here, right? Okay. So let's see if we can figure out why this is 0, because there's lots of stuff in here, correct? But notice again, this has m's and n's in it, and it doesn't necessarily understand what we mean by m and n, right? It's trying to treat them as variables, doing it symbolically. But we know that m and n are what? What kind of objects are m and n? What kind of numbers are they? Integers, right? So this is always a multiple of 2 pi. This is always a multiple of 2 pi. When I add two multiples of 2 pi together, I get a multiple of 2 pi. What is cosine of 2 pi anything? It's always 1, right? So that first part right there is going to be negative m on top, right? That part will be negative m, okay? This part here, if I do, again, multiple of 2 pi minus multiple of 2 pi, still a multiple of 2 pi, so that's cosine of that again is going to be 1 again, right? So we're going to get another minus m, correct? What do you notice in the next term? Plus 2m. So those are going to go away. It's good, right? We want everything to be 0 by the time we're done here, correct? Okay. All right, so let me see if I can, I don't know if I can scroll over enough or not. I don't know if it'll let me. Oh, it does have a scroll bar down here. What do we notice in the next one? Again, this part, this is cosine of a multiple of 2 pi. That'll be 1. So I just get n. What do we get in the next term? Minus n. So that's also 0. So we really do get 0 for this whole thing. Okay. So this, notice I did it this way so you didn't do it by hand, right? Okay. There are special formulas. There are trig identities that you can use to rewrite these and do the integrals quickly. Remember your sum formulas for sine and cosine? Yes, Dr. Joe, I remember my sum formulas for sine and cosine. Okay. You rearrange the sum formulas for sine and cosine to rewrite something like this as a sine of a single thing or cosine of a single thing to be able to do the integral. The whole trick of that. Remember, just to show you what I mean by this. Do this on the board here real quick. Everybody's looking at me like I'm nuts. if I had cosine of m plus nx, you could write that as cosine of mx cosine of nx minus, leave myself in room, sine mx sine nx. Remember those? All right. Okay. That one, right? Okay. Okay. So if you wanted to, say, get something that looked like, integrate something that looks like that, the sine mx cosine nx like we just did, the trick would be to do the subtraction, which of course flips the sign in the middle, add them together to cancel those terms out, and then divide by 2. So you would have sine of mx cosine of nx is 1/2 sine of m plus nx plus 1/2 sine of m minus nx. And now those are things that you can integrate easily. That's the trick for doing those. So if you've got sine of m cosine of n, you use this one. If you had cosine cosine, you would use this one. If you had sine sine, you would use this one. And try to make the other term go away. Didn't say it was horribly fascinating. I'm just telling you what you would have to use to do it by hand. Okay. All right. Anyway, I'm not going to do any more of that. But this is how you would check to see that you really do have an orthogonal basis in this particular instance. All right. So let me go back over to the notes. Maybe. All right. Go back over to the notes here. Then this set, let's back off. This set is an orthogonal set. We can check, we only checked one, right? We did sine of something times x times and a cosine of something times x, right? You should check your sine with another sine if they're different m and n, and you should check a cosine with a sine, or cosine with another cosine with different m and n. I didn't check the one either, did I? But if I integrate any of these from 0 to 2 pi, I'll always get 0. 1 times that will give me 0, so I always get 0. So these really are orthogonal to one another. Okay? So if you have another function, so if f is periodic on the interval from 0, we start with 0 to 2 pi. We'll talk about how to change to other intervals, intervals. Good Lord, I want to say integral and interval at the same time. All right. If we have a function that's periodic on the interval from 2 to pi, and we want to approximate it with a trig polynomial, then we need to compute the projection of f onto the space W. And W is just the space that's generated by all these trig functions that I gave you. Okay? Okay? We'll have to compute that projection. What we just did before is that we have to do the inner product of the f with all of those, and then divide by the inner product of all of these things with themselves, right? So the way we have that, I'll just write it this way to start with. I'll write it as f dotted with 1 over 1 dotted with 1. times a 1, right? And then you'll do f dotted with sine of x over sine of x dotted with sine of x times sine of x. Do the same thing with cosine. And you continue forever if you're going to find the series. Now remember, those things on bottom are not multiplications, or the dots are not multiplication symbols. Those are referring to a dot product, an inner product. Okay? I'm being lazy with the notation. I really should use the pointy bracket notation for inner product like we've been doing in linear. But I don't care as much about all the concepts of inner product here because we're just using it to help us. All right, so again, we want to find the projection of the function onto the space. I'm using W to denote the set of all possible linear combinations of anything out of that big long set that I talked about. Right? All right. So then the projection of f onto that space would be that infinite series. And this is what we mean by the Fourier series, by computing those things. Okay? But let's see if we can actually write down the formulas for each of these coefficients so that we're not redoing this all the time. Okay? In particular, notice that the only thing that ever changes from problem to problem is f. Right? That's the only thing that ever changes is the f, correct? Okay? In particular, these denominators are always the same. Okay? So let's see if we can figure out what those denominators are. I'm going to do that in GeoGebra because I'm lazy. I don't feel like integrating that by hand. Okay? Sound like a plan? Okay. All right. So back over to GeoGebra real quick. Pop back over here. Scroll over. All right. I want to do the integral of, let's do all of them at once for sine and all of them once for cosine, okay? So I want sine of x times sine of nx times sine of nx, same function, right? So it's sine of nx squared. So I want to write parentheses around it, sine of n times x squared. That's the function we need, right? That's sine, the inner product of sine with itself. Yeah, okay. Again, I've got two variables in there. I've got an n and an x. We want to integrate this with respect to x, so I tell GeoGebra what variable I'm integrating with respect to. And again, the interval is 0 to 2 pi. So we do interval from 0 to 2 pi. Okay. This is a wonderful little program because I'm not integrating all this crap by hand. Okay? All right. And it's free. That's the best part about it. Now, sometimes it's clunky and doesn't want to work right, like it was doing to me in my office before class today, and about threw the computer through the wall, but that's neither here nor there. Okay. All right. Let's analyze this now because I want to try to simplify it. That's going to be our goal in lots of these problems when we're trying to find these series, is trying to see if we can simplify it based on what we know. What kind of a number is n again? Integer. So the thing that's on the inside of sine there is a multiple of, it's a multiple of 2 pi, which is an important part, right? Sine of 2 pi is 0, right? So this goes away, right? The first term here goes away. Then your n's cancel and your 4's cancel, and all we're left with is pi, right? So that's what we just found, was when we do this integral from 0 to 2 pi of sine of nx squared dx, we always get pi. So back in the formula that we had in our notes, back in the formula that we had, the denominators for any of those sine of x dotted with sine of x, or sine of 2x dotted with sine of 2x, and so on up the line, the denominator is always pi every single time. Okay? Let's do the same thing for cosine. Integral function. We want to do cosine of nx squared from 0 to 2 pi. Same exact syntax. All I did was just replace sine with cosine. That looks familiar. It's the same answer, except that there's not a negative in front of the sign anymore. But does that matter? No. So that's also pi. So this tells us that our integral from 0 to 2 pi of cosine squared of nx dx is pi. So notice that those, pardon me, notice that those denominators every single time are pi, except for one of them. And we'll see which one it is here in a second. But when we have those combinations, we always get pi. Is that okay? Like I said, that saves work. I know what the answer is every single time. Right? Okay. So let's go back over. All right. So again, all of these denominators. This denominator is pi. This denominator is pi. That one's pi. That one's pi. So on up the line. All of them are pi except for one of them. We didn't do that one, right? But if I want to integrate one with its, if I want to do the inner product of one with itself, that's just integrating 1 over the interval from 0 to 2 pi. What do I get? 2 pi. It's double, right? Okay. So notice that one turns out to be 2 pi. So this is leading us towards how we figure out what our coefficients are. So when we have a Fourier series and if it converges, our f here will be written in the form a naught over, I'll write it as 2 pi, because that was our denominator, right? Okay. Plus 1 over pi times the sum n equals 1 to infinity of what? Well, sorry, I'll write it this way first. A1 sine. Oh, I don't want to mess you up with the letters. Doesn't really matter. I think these are actually the cosines. I just want to make sure I'm consistent with the lettering. All right, so this is what we look at for a Fourier series. Oh, nope. I'm going to erase something. Sorry, I hate when I do that. I just forgot that they put the pi in the formulas. They write it this way. Sorry, I just remember that they put the pi's in the formulas. This is what they write for the Fourier series. Notice it's half of the first one, for that's the 2 pi. So your A's, your A naught, of course, is your integral from 0 to 2 pi of just the function. Oh, crud. I got to go back and fix something real quick. Those are n's, not ones. Told you I was frustrated this morning and I didn't think about exactly writing this down when I came inside or came into class. Your A naught, of course, is just your integral from 0 to 2 pi. It's 1 over pi of f dx. Your A sub n will be your 1 over pi integral from 0 to 2 pi of f of x cosine of nx dx. And your b sub n will be 1 over pi integral from 0 to 2 pi of your f of x sine of nx dx. writing it in this fashion, I really could have combined these first two together, because if your n is equal to 0, what is cosine of nx going to be? If your n is equal to 0, what's cosine of nx going to be? Just 1, right? So I could have combined these two together to give you the same formula. But ordinarily, well, a lot of times we'll just do them separately. But anyway, when they write down these numbers, they put the 1 over pi in front of the integral so that you remember what the formula is, I guess, that way. It doesn't really matter. We refer to these as the Fourier coefficients. And these are what we have to compute to be able to get the series. Okay? Well, if we wanted to actually write down the infinite series, we're going to use these integrals, leaving an arbitrary n in there, to get a formula in terms of the n. All right. So let's see if we can do a quick example. We'll do several examples, but let's see if we do a quick and easy one to start with. At least I assume it's quick and easy. Let's say our function is -1 from 0 to pi and 1 from pi to 2 pi. And then it repeats. All right, so at 0, we're down at -1, and then to pi, we stay there. And then at 1, we jump and go over to 2 pi, and then we, how did I write that? This fills in here. This fills in here, and so on down the line. So since it's periodic, it's going to keep bumping up and down. So over here, it'll be up here, and then down here, it'll be over there, and continue that pattern. This function's not continuous, right? Definitely not continuous. So it definitely will not be in the space generated by those trig functions, no matter how many trig functions I've used, right? What our goal here is to try to approximate this idea using a trig polynomial. See how good we can get to an approximation. Okay? All right. So, we got to calculate all of these coefficients to try to write these things down. Okay? So, this is why I said we're going to use GeoGebra to help us with the computations. So, let's go over and do that. Not that this would necessarily be that hard to do, but just to get you in the practice for it, for what we need to do. Notice that when we're doing the Fourier coefficients, I just need to integrate the function over the interval. And then I need to do the function times sine of nx over the interval, and then cosine of nx over the interval, right? The function times cosine of nx over the interval. Well, hopefully let me go back over real quick to the function. Hopefully integrating the function over the interval is easy in this case. From 0 to pi, it's down at -1. From pi to 2 pi, it's up at +1. What's the integral of the function from 0 to 2 pi? 0, right? It's going to cancel each other out, correct? So our integral from 0 to 2 pi of f of x dx is going to be 0 in this case, right? Okay. All right. So let's see if we can do the other ones. Notice that it's going to be a piecewise function, right? From 0 to 2 pi, we've got to integrate the negative of sine nx, or the positive of cosine nx, or positive of sine nx for the second part, and then so on for the cosines. So I need really to do a couple of integrals for the first one here. Let's do that. I want to do the negative of sine of nx. That goes from 0 to pi. That's the first half of the interval, right? Right? It was -1 for the first half of the interval. And then in the second part, we'll do positive sine of nx from pi to 2 pi. All right. So again, these two pieces together are doing this integral. Right? Those two pieces together are doing that integral. We have to split it into two because we have a piecewise defined function to start with. All right? But to get this integral, what do I need to do with these two answers? Add them together, right? When I add those together, what are we going to get? We're going to get some things with cosine in here. But notice this one. What does cosine of n pi do? Let's start there. What does cosine of n pi do? Yeah, -1, +1, -1, +1, it alternates, right? That part alternates. So what is cosine squared of n pi going to be all the time? 1. All right. So that part's going to simplify to -1, isn't it? Notice everything here is over n. I'm just trying to get a sense of what's going on. Yeah. Okay. That part's going to be -1 when I put those two pieces together. We also got another -1 here, don't we? Okay. And then finally, this part here is going to be just 2 cosine of n pi. Right? So what's this is going to alternate back and forth between. This is going to be -1, +1 times 2 will go between -2, +2, right? So when it's +2, the whole thing will be 0. Yeah? And when it's -2, we'll get -4 on top. Okay. So in any event, we're just going to try to get a picture of this thing. We'll worry about doing some more simplifying later. But this is what this would simplify to. You'd have -2 plus 2 cosine of n pi all over n. Right. So we have so far. Yeah. Yes.
Where did the +1 go?
+1 -2. Yeah. Yeah, I did that -1 first from that one. Yeah. All right. So this isn't quite your b sub n. Right? What do we have to do with this to get your b sub n, the coefficients on the sine piece? What goes out in front of all your integrals? 1 over pi, right? So if you want to do your b sub n from here, I'd have a pi on bottom. Okay. All right. We need to do the exact same thing for your cosine. Literally, exact same process. But I'm just going to change the sine of nx to cosine of nx. Literally nothing else changes. Okay? Integral negative cosine of nx. X goes from 0 to pi. And then integral of cosine of nx. And then again, x goes from 0 to, pi to 2 pi. What are both of those going to equal? Both of those are 0, aren't they? This is always a multiple of pi, well, multiple of 2 pi. That's always a multiple of pi. That's always a multiple of pi. Sine of a multiple of pi is 0 every single time, right? So your a sub n's, all of your a sub n's are 0. By the way, that's not that surprising. Let's go back over to the picture. Speaking from symmetry, what kind of a function is this? Think about your symmetry that you can have for a function. What kind of function is it? Yeah, it's odd, isn't it? Notice that if I turn it upside down, I get the exact same graph, right? Whatever is below the x-axis on the right has a mirror image above the x-axis on the left and vice versa. when you integrate those, when I have an odd function, if I'm trying to approximate this odd function with sines and cosines, well, we know that sine is odd and cosine's even. Notice that all that's left are the odd pieces, right? All the even pieces went away. That makes sense from the way the function looks, right? If I'm going to try to approximate this function with sines and cosines, and the function starts out to be odd, then I would anticipate the only thing in it's going to be sines. If it were an even function, you would anticipate the only thing in it's going to be cosines. Yeah. And so you can tell that from some of the symmetry ideas. So that matches up with what we know from the symmetry of the function to start with, which makes sense. Okay. These are good checks to do. These are good conceptual checks to do as you're going along. All right. So let's see how well we've approximated this thing. So let's see if we can get a graph. All right. So here's how we'll get a graph. It's harder to see down here. Because I got that thing blocking the way. All right, to get this, at least from what my experience has been with GeoGebra, if I'm in my computer algebra system window and I want it to graph the expression that I have, I need to define it as a function. So I've typed in f of x here, and then to tell GeoGebra I really want to define this as a function, I use a colon equals in there. So right now what I've typed in is f of x colon equals this thing. Okay. Remember again when we're doing our Fourier series, the formula looks like a naught over 2 plus the sum from 1 to infinity of an cosine of nx plus bn sine of nx, right? That's what our formula looks like. We just said that our a naught was 0. That went away, right? And that one also went away. So the only thing I really need to worry about is this. Okay. So I'm gonna stop this at a certain point because I want GeoGebra actually to graph it. I want to see what the graph looks like, right? That's the idea. We're going to use the sum command. So if I type in sum, there's all sorts of things in there. Hey, notice there's also a sum of squared errors in there. That's kind of fun. No one cares. Okay, great. Let's not connect it to stuff that we've done. All right. The second one is the one that we want. I want to type in an expression, tell it what variable is changing, where to start, where to end. Okay? All right. The expression we want is this b sub n times sine of nx. We want to create a function of x, right? So this is what we found for our b sub n. So what do we have? Parentheses -2 plus 2 times cosine of n pi. That was what we came up with, wasn't it? On the top. Making sure I'm in the right spot here. Over. Couldn't tell what the parenthesis was. Over n times pi is what we said that was. And again, those are our coefficients on the sine pieces. So I'll multiply that by sine of nx. Right? Sine of nx is what we're multiplying by here. This is the piece that we had left. Okay? The variable that we're changing is n. We start at 1, because remember the constant term is handled separately. We've got to divide it by 2. Right? So we started at 1, and then just end it somewhere. So let's say we want to use 10 terms. Just arbitrarily pick one. Okay? Because if the more terms you pick, the better the approximation is going to be. Okay? Obviously. Well, not obviously, but hopefully the more terms you pick, the better the approximation will be. If you think about it like you do power series, right? Same idea. More terms get you better accuracy. Let me hit enter. Let me scroll back. So notice that we're down here at -1 for a while. We're up here at 1 for a while. We're down here at -1 for a while. Of course, what's it trying to do in between? It's trying to connect them, isn't it? Because again, we're trying to approximate a non-continuous function with a continuous one. So there's going to be issues where you have jumps. Okay? So the approximations here in the middle, you would expect to be much better than they are near those endpoints where it jumps. Because again, the function's got to get from down here to up there. Okay? Yeah, Ben.
Why isn't it a simple, or a much simpler, should I say, sine more looking graph than that?
Well, it's trying to approximate the function as best as it can. So the more terms you get, actually, we should get more things that are closer to ones and negative ones in between. It's what it's trying to do. Is trying to approximate the function as best it can. So let me change that number. Instead of using 10 terms, let's use 100 terms. It'd be a sine curve. Yep, you got it. Yep, that's exactly right. So notice here again. Look at you can see it waving, right? You can see the little bitty bumps in there, right? And then gets here towards the end. It's like, oh crap, I'm hitting a discontinuity, right? So it gets worse here, jumps, and then oh hey, good, I'm happy. Oh crap, close to another one, and it jumps again. Again, these kind of functions are used to approximate these kind of wave ideas. So this would be referred to as a square wave. You can think of, well, this one's not quite the right thing, but again, you can think of this as kind of on-off, right? Or maybe positive polarity, negative polarity, positive, negative, switches back and forth, kind of thing. Okay. Again, you can think of this as being something that periodically switches whatever it is, switches from one to the other instantaneously. So this is the idea behind doing this. Again, the problems are all exactly the same within reason. I mean, if we've got a different period, we have to do some adjustments, but we can talk about how we can change the period. But these problems look exactly like this every single time. Okay. Again, notice we have a non-continuous function, so we would never, ever, ever expect these continuous functions to exactly match the function we're given, right? But it's certainly really, really close, especially in the middle, which is probably where you're trying to approximate it anyway. I think I've mentioned this before, endpoints suck, right? Endpoint things are hard, which this is just another example of endpoints are hard. There's a lot of analysis that goes into trying to figure out what happens near boundaries. Boundaries are bad, just generally speaking. All right, so let's see if we can do another example. Let's see if we can create the Fourier series. But let's shift our interval instead of going from 0 to pi. Let's say our function is x plus let's do x plus pi from negative pi to 0. Oh my heavens, I was right. Let's go x plus pi from negative pi to 0, and then let's do pi minus x from 0 to pi. So it's still a 2 pi interval, but we've shifted it a little bit. Okay, so we haven't changed the period. We haven't changed our period from 0 to 2, for our 2 pi period at all. So our functions, our sines and our cosines that we came up with before, should still work on that period, right? Sine of x and cosine of x are functions with period 2 pi. All we've done is shift. So the only thing that's going to change when we calculate our coefficients here is that when we do our integral for a sine or cosine, what do you think is going to happen to our limits? Before we used 0 to 2 pi, I mean negative pi to pi. Good. Right? That's the only thing that's going to change. We should also check our coefficient out in front. That might change depending on the period. Right? But our period is still 2 pi. So our coefficient out in front is still going to be 1 over pi. Okay, literally, if I still have a period of 2 pi, and all I've done is shift, the only thing that changes are your limits of integration. Okay, nothing else changes. All right. So let's see if we can create this one. Again, for both of these, we'll have to do. Let me reload this so that I can go back up at the top of the screen here, so that you can see what I'm typing rather than look at the bottom. All right. Again, this is a piecewise defined function, so we'll have to do it in 2 pieces. All right. One of those pieces is integrate the function over the entire interval, right? That's where our A0 comes from. So we'll integrate x plus pi from 0 to, from negative pi to 0. Notice if there's only one variable in there, I don't have to just specify what the variable is. It doesn't hurt. If I would have put a comma x in there as well, it would have been fine. Okay. And then the other one would be pi minus x from 0 to pi. Right? Okay. Add those together, you get pi squared. Remember, though, that the coefficient out in front of that one's you divide it by 2 pi, right? All your Fourier coefficients get divided by 2, and your constant gets divided. All your Fourier coefficients get divided by pi, and then the constant term also gets divided by a 2. Remember, it was A0 over 2, right? Okay. So your A0 in this case then will be pi squared over 2 pi, so we'll just get pi over 2. Okay? Okay? All right. Add those two together, we got pi squared, we divide it by 2 pi. We get pi over 2. All right, need to do the other ones. Let's do our integral of, first we'll have to do x plus pi times sine of nx. Because this is the first half of the function, right? Going from negative pi to 0. Right? I have to multiply the function times the sine of nx. Do the exact same thing, except do the second half of the function from 0 to pi. So let's get that one, and then do pi minus x sine of nx with respect to x from 0 to pi. What do we end up with? You get 0, right? The sine of n pi's are 0. Those go away. In the first one, you've got a minus pi over n, and the second one, you've got a pi over n. So I get 0. Again, if I think about this from a symmetry point of view, this is not a huge surprise. I rigged it. If I were just to graph this function and not worry about the periodic part, I made that function. That function's even, so the sine pieces went away. Right? I did a line that sloped up to pi with a slope of 1, then sloped down from pi with a slope of negative 1. So again, I rigged it so it was even, so those pieces went away. That makes sense? Okay. All right, so let's do the cosines. I'm just gonna, since I don't need those, though I know this is 0, I don't need them. I'm just gonna go back up and edit these. If I click in the cell, I can just edit it pretty quickly. That one I need cosine. Just do cosine. Yeah, do cosine. Great. Go away. What are you doing? This is what I was doing this morning. There we go. Got that one. Finally. This one I need to do. Oh, no, it didn't do that one. What are you doing? I don't know why it's doing that. Sorry about that. This has got extra on the end too. Gets cranky. There we go. All right, so again, I just changed the sines to cosines. I'm getting rid of that cell at the bottom here. Just change the sines to cosines. Notice we have the same answer both times, right? So basically, it's just double this, isn't it? So again, we'll have a 2 minus 2 cosine of n pi over n squared. But what do we have to divide this by again? Pi again, right? Because all your Fourier coefficients get divided by a pi, except the constant one gets divided by 2 pi. All right. So now if we're ready to create our function, let's just delete this row. I'll call it g of x this time because I already defined an f of x. So our constant term was pi over 2. And then we'll put in a sum. We just said that we'll have 2 minus 2 cosine of n pi divided by n squared times pi, right? We'll multiply that by the cosine of nx. Oh, good grief, go away. Trying to unblock it, not block it. Again, when we added these two together, it doubled the top, essentially, right? So we've got 2 minus 2 cosine of n pi. The denominator is n squared pi, because again, we divide that thing by pi. 1 over pi is always in front of the integrals. And then multiply by cosine of nx. The thing that we want to change is the n. And this time, let's do 1 to 10 again just to start to see what it looks like. And then we'll change it. It's pretty good. At least I think it's pretty good. Now notice that this one looks better even with fewer terms because I started with a continuous function. That's actually in the continuous function spaces, right? So this should be able to do a better job of approximating more quickly because it's approximating something that looks like the kind of thing that those functions are. They're continuous, right? So it should go a little bit faster. Not be perfect. Notice that it has issues here where we've got those sharp corners. Makes sense. Those are boundaries again, right? I should have issues near those boundaries. Okay? And again, notice we're trying to approximate a function that doesn't have derivatives at certain points with functions that are differentiable everywhere. We should expect issues near those points where the derivative doesn't exist. All right. Again, this one looks like I said looks pretty good, but if you wanted to see even better, see what happens if you try 100 terms. Now it's getting pretty good with the corners. It's just doing it really. It's just turning really fast. Right? It's getting pretty good. But you see, it's still not perfect. When we zoom in. And again, not a huge surprise. It's never going to be perfect. All right. Any questions on that one at all? That one looks pretty good though. If you zoom out, that one looks pretty good for what you would expect it to look like. So we got this thing bouncing up and down kind of thing with the corners on it. This to me is the fun part of doing these things. So you see these functions that pop out, these different graphs that pop out. Any questions on that one at all? Yeah, thanks.
So is like the final answer that we're looking for the g of x that we typed in?
Yes.
Okay.
Yeah, the series that we're looking for. Yeah. Yeah. So we can actually write it down as an infinite series at that point, because our infinite series then would be. What did I say? N squared pi. Like that. Goes way ahead. Okay. We could make this a little bit better. If we wanted to make it a little bit better. Notice that, again, when your n is even, this is going to be 0. So the only terms we're going to get are the odd ones that pop out. So you could rewrite this. When it's odd, this becomes 4 on top, right? It's a 4 or it's a 0 or it's a 4 or it's a 0. That's all you ever get's a 4, isn't it? Okay. So this would be 4 over pi sum n equals, I'll do 1 to infinity. And then this would be 1 over 2n minus 1 squared cosine of n x. Not bad. I adjusted here to make sure that I only get odds. So I could do a 2n minus 1 or a 2n plus 1. I did a minus 1 here because I need the first one to be, if I start this at 1, I need this to be a 1 to start. So I've got a 2n minus 1. So I can write it this way. So this actually is I'll just do this in the last 4 minutes because that sounds like fun. Okay. This actually allows you to get some different identities of things that add up. Because now I can get some actual infinite series of numbers that add up to different things. So remember again, this is equal to, I wrote g of x. This is my f of x here. So I wrote g of x in GeoGebra, which is why I rewrote it here. This should be equal. In particular, if I put in 0, I should get a true statement, right? I should get a true statement. When I put in 0, we get pi out of that side, don't we? Yeah. On the right-hand side, what do we get when I put in 0? Well, what do I get here when I put in 0 for x? What do I always get? 1. Right? So I can subtract my pi over 2 over. Get that. And then I can solve for that series. And then I've got a nice little formula. This is the sum of what? 1 plus 1 over 3 squared plus 1 over 5 squared, 1 over 7 squared. So doing these Fourier series ideas can also get these kind of identities. That's kind of fun, isn't it?
Can you solve almost any infinite series like this if you can figure out how to put it into?
You can do a lot of them, yeah. You can do this with, there's a reason why there's a whole formula for these things. So if you do this one, we're not going to go through this. We have to create the Fourier series correctly. That one's pi squared over 6. So if you can figure out a Fourier series that works for x squared, for example, you can get this one. What's interesting about these, any even power, there's a formula for it. You can do any even power. Odd powers, can't find a formula for them. You don't know what it is on this side. So 1 over n cubed, can't figure that one out. Or at least no one has figured that one out. I don't know if it can or not. I don't know if it's impossible or not. It just hasn't been proven that it's possible. Right. It's kind of weird. But those are kind of fun. So we'll play around with some more of those next time as well. So we'll talk about next time more examples of these. In particular, what happens if we want to change the period to something just besides 0 to 2 pi. Not a big deal. We have to make constant adjustments, but same process. I promise you that the process every time will be doing these integrals. If you've got homework sheets for me, if you got the Excel too, that'd be great. Yeah. You email that Excel. Thank you. Thank you. Thank you.
I thought about printing it out, but I couldn't sure remember anything.
I did, yes, thank you.
I felt bad. I left my folder.
Oh.
Because I was working on it last night and I forgot to put it back in the backpack.
Just get it to me. Okay,
I did.
Here, I'll find it. Yep.
I'm dragging Zoe along to go see that. You'll have an audience.
Wonderful. I've already been told